Hello, good morning, bonġu. Tisimawni? Alright, mela. Tuni ftit zaħira ċansta. Alright. Mela, alright. Illum ħankomplu naħdmu daqsxejn fuq linear motion. Issa ma qabel rrid ngħidilkom li ħantikom issa tuni ċans għax mill-bieraħ għalaw xi affarijiet. Mela, ħanurikom daqsxejn, ma intom siksej, ġvera. Alright, mela. Fuq il-VLE, alright, i-postjajt l-assignment aħna l-bieraħ l-istejna il-tutorial fuq vectors u ġvera. U postjajt assignment li qiegħed hawnhekk dan vectors and scalars assignment, ok? Għandkom sa bħallum ġimgħa sa Thursday 26 November biex ittu li lura. Biss ħudu daqsxejn paċenzja. Tibdewx taħdmu fuqu minn issa bdew waħdmu fuq il-lejla għax irrid nirranġa ħarira. Alright? Issa, biex ngħidilkom ukoll, biex tkunu tafu wkoll, il-bieraħ kellna insomma laqa il-teachers tal-physics, alright? U kif kont għattilkom fil-bidu tas-sena, nista' nikkonferma li ħajkun hemm apparti il-homeworks li ntikom jiena, kultant ħantikom xi ħaġa żgħira mhux twila ġifieri, xi ħaġa żgħira mill-past papers ukoll li tmur għall-assessment li tkun importanti ħafna, right? Li di nagħmluha bħala question tkun question insomma li toħroġ mod uffiċjali ħanejdu għaj. Issa, il-choice hija li ma nibqax intikom homeworks jew naħseb jiena ma practice għandkom bżonn xorta ġifieri homework xorta ħanibqa' ntihom u l-marki xorta ħanżommhom biex ikun nista' nużomm. Alright? Ġifieri dal-assignment ħantihulkom xorta naħdmu fuq ukoll, imma biex tkunu tafu stennew li iktar il-qudiem ħantikom questions, alright, ikunu questions żgħar li tkunu tridu taħdmuhom ukoll u tuhomni. Ok, meta ntikom daw it-tip ta' questions ukoll il-time limit ma jkunx daqshekk twil. Alright, ġifieri mhux se ntihomkom għal ġimgħa sħiħa, intihomkom pereżempju fil-bidu tal-ġimgħa u niġborhom fl-aħħar tal-ġimgħa mhux inħalli 7 whole days. Tajjeb, imma biex tkunu tafu li għattilkom is-sistema għaw is-sitwazzjoni qiegħda tinbidel il-ħin kollu qed jittieħdu deċiżjonijiet kontinwament, m'għandix kontroll fuqhom, jiġifieri prattikament daqskom naf, biex tkunu tafu, alright? Ġifieri iktar qudiem meta ngħidilkom dil question importanti u għandi bżonn niġborha within 3 to 4 days, dik tkun question li tridu taħdmu fuqha kemm jista' jkun malajr u tuwili lura, dik tkun importanti jkollha weight iktar minn daw il-homeworks li qed intikom jien. Alright? Biex tkunu tafu. Mela, alright, ħankomplu issa fuq Iva, kif għattilkom il-homework ħanbiddel xi ħaġa żgħira minnu, ħabba li nqalaw li ma nqalax. Mela, ħankomplu daqsxejn issa it-topic li konna bdejna l-aħħar darba. Għajdli.
Jake Zammit qed jgħid li qed ikollu problemi jidħol qed jgħidlu error.
Ħanejlek fil-każ għajdlu jrid jagħlaq iż-Zoom totali għax bħalma ġra lil bieraħ jiena. Li jalaq totali Zoom kompletament u jrid jerġa' jiftaħ kollox mill-bidu. Għax il-bieraħ hekk għamel li wkoll. Alright, mela. Okay. Mela, aħħar darba wasanna. Sawnik. Okay. Mela, l-aħħar darba bdejna nitkellmu fuq linear motion, tkellimna fuq kif insibu il-velocity. Alright? U rajna li l-velocity ħanerġa' nfakkarkom ftit. Rajna li l-velocity, il-definition ta' velocity hija the change in displacement over the change in time. Alright? Allura ktibnija change in displacement over change in time. Rajna li nistaw nikkalkulaw il-change in displacement kif konna t-namlu vectors, ġifiri namlu bħalma rajna hawnhekk fejna. Hawnhekk, alright? Ġifiri biex namlu change in displacement, rridu namlu mpinġu l-final kif inhu. Bħalma minnaw. Impinġu l-final kif inhu, mpinġu li nixxiel bil-kontra u noddu. U dak jiġi di change in displacement. U tista' titfaw hemmhekk. Rajna li it's a time-consuming method, alright? And since in linear motion we're going to work in most cases in one dimension, so just in one dimension, it makes sense that instead of using this method to calculate the change in displacement, we can use signs. U hawnhekk bdejna nużaw is-signs. Remember that the plus and minus sign represent only the direction. Plus to the right, minus to the left, and that's all. Alright? Plus to the right, minus to the left. Issa. So, this is the formula of displacement, but this formula of change in displacement over change in time can only be used if we have a constant velocity. Ħaniprofa nfehmkom ftit fuq għadi. If we have a constant velocity, why? Because while using this formula, I am assuming that during this time interval, delta t, alright, the change in displacement was changing at a constant rate. If the velocity is not constant, so the displacement is changing at a different amount of displacement, you have a different change in displacement in a certain time interval. So if during that time interval the velocity is changing all the time, I can't find that the velocity is changing using this formula. Għax inti kull ma ħatamlu huwa change in displacement over change in time. So if during that interval of time the velocity was changing, I will not musa ninduna biha. Alright? Ma nistax ninduna, edin tifmuni x'qed ngħid. Għax waqt dak it-change in time inti ġast se tuża l-formula. Mela. If during a certain interval of time the velocity is changing and I still use this formula, in that case you would be finding the average velocity during that interval of time. Edin niftehmu. So, can I find the velocity at a point in time when the velocity is changing continuously? So if the velocity is changing continuously, is there a method how I can find the velocity at an instant in time during that period of time? Edin tifmuni x'qed ngħid? Edin tifmuni? Now, the only way how to find this type of velocity, which by the way is called the instantaneous velocity. The definition of the instantaneous velocity is the velocity at an instant in time. This is the definition of instantaneous velocity. It is the velocity at an instant in time. Instant in time, mhux qed ngħid sekonda jew minuta. Instant in time, at an instant, at a very instant in time. Now, the only way how you can find the instantaneous velocity at a particular time while the velocity is changing all the time is by using this formula that I have up here. But the change in displacement and the change in time should be very, 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 very small. Very small. Biex inti meta inti qed tagħmel dak il-change in displacement dak il-change in time, mhux qed tilħaq il-veloċità tinbidillek, qegħdin niftehmu. Mela dik il-change in displacement and change in time should be very, very, very small. And the only way how to do it is by changing the formula in this format. X'għamiltaw? Mela, sissa tidher li jisni m'għamil xejn. Alright? Tidher li jisni m'għamil xejn, imissa kif ħadd indunaw iktar il-qudiem, di ħadd tfisser ħafna. When I write the formula for velocity as ds by dt instead of delta s by delta t, what I'm doing is I'm changing delta, which is a large capital D, mhux vera, to a small d. When I use a small d, it means a very, very small change in displacement over a very, very small change in time. So what I'm saying is, if the velocity is changing all the time, you can't take a large interval of time and a large change in displacement and calculate, because in that case, you will be finding the average velocity over that period of time. To find the time, the velocity at an instant in time, at a particular instant in time, you need to decrease that large amount of change in displacement and large change in time to an instant in time. Now, how can we do this in practice? Because in practice, how can I find the change in time and the change in displacement at an instant in time? Qegħdin tifhmuni huwa mhux laqqas fraction of a second, at an instant in time. Mela, there is a mathematical method how to do this, which is called calculus, which you will be doing at A-level or intermediate mathematics. I'm not going to use calculus in this case, alright? Because we're not going to use mathematics at A-level standard, alright? We're going to use only mathematics at O-level standard. But there is another method, which is a very straightforward method. How we can still find the velocity at an instant in time when the velocity is changing, alright? Without using calculus, but using a graphical method. Alright, but I'm not going to discuss it right here. For now, it's just important to know what instantaneous velocity is. Therefore, we can use this formula whenever we have constant velocity. So whenever we have a constant velocity, we can use this formula. Sound alright? Kulħadd alright? But when we don't have constant velocity, when the velocity is changing all the time, to find the instantaneous velocity, we have to use the velocity in calculus notation. But for now, you don't know the method. I will explain the method later on. Alright? Actually, this is the official way how to write down the formula for velocity, because that's the most in general formula. Even if the velocity is changing, that is how you can find the velocity at a point in time. Sawnek alright? Naf li tal-instantaneous għal-issa tkun ma mintomx forsi tifhmu għal-sew, issa tifhmu ftit iktar qoddim. Mela, okay. So, till now we discussed two physical quantities for linear motion, displacement and velocity. Now we need the third physical quantity, which is very important to understand before continuing with linear motion, which is acceleration. So, let's check exactly what acceleration means. So, acceleration happens, we obtain acceleration when an object is changing velocity. So, if I have an object and at 0 seconds, the velocity is 0 meters per second. At 5 seconds, the velocity is 4 meters per second. And at 10 seconds, the velocity of this object is 8 meters per second. Sound right? So it is very clear that this object is not moving at a constant velocity, so I can't use this formula, alright? But it is changing velocity all the time, alright? It is changing velocity all the time. When velocity is changing, there is a physical quantity which is called acceleration. And the definition of acceleration is the change, is the rate of change in velocity. So, what does the acceleration give us? The acceleration gives us the amount of velocity that is changing every second. Ġveri għanna 3 livelli. Mela bdejna bid-displacement, which is just the position where the object is from a reference point. Imbagħad rajna the change in displacement per unit time, the rate of change in displacement. That's the velocity. So how fast we are moving, the amount of meters covered per second. Now we have the third level, which is the acceleration. The acceleration doesn't give us any information on how fast the object is moving. That's velocity. The acceleration is only giving us information about how fast the velocity is changing. Alright? So you can have a very fast moving object, but the acceleration is slow because it's not changing so much, the velocity. Bħal per eżempju, bħalma jkollna jinnaf when you have a spaceship moving at constant velocity in space, for example. Alright? You have very large velocities, but the acceleration is zero. Ġveri, l-acceleration ma tatinix informazzjoni fuq how fast the object is moving. That's velocity. The acceleration gives us information about how much and how much fast the velocity is changing. Alright? Mela għandna informazzjoni fuq how the velocity is changing. So that's why it's called the rate of change in velocity. The formula for acceleration is very similar to that of velocity, but it's the change in velocity over the change in time. Alright? So let's try using it. How are we going to find the change in velocity? Issa, kif insibu change in velocity? Diġa diskutajni ħafna drabi di. Final minus initial. So I'm going to use final velocity minus initial velocity over the change in time. Issa, you should know already the symbols used for final velocity and initial velocity. Ux tafuhom suppost. Final velocity, the symbol is V. And for the initial velocity, U. Tafu għaliex U V? L-alfabet wara xulxin. T, U, V. U, V. U l-ewwel waħda, V l-tieni waħda. Naqseb kollox. Alright? Ġifieri U is the initial velocity, V is the final velocity. That's all. Because they are after each other in the alphabet. Mela, ejja ħanippruvaw. Now, I'm not going to draw the vectors. I'm going to use the signs. Alright? Because now we're in linear motion. We have only one dimension. Therefore, I can use signs. Mela, let's try to find the acceleration from this part. Alright? From that part. So, the final velocity in this case, which one is the final velocity? The 4 or the 8? 8. So that's the final. And this is the initial. Mela, 8 is positive or negative? It's pointing to the right.
Positive.
Positive. Mela na plus 8 minus, and the initial is plus or minus 4?
Plus.
Plus 4. Because it's pointing to the right. The change in time, I have 10 seconds, here I have 5 seconds, so it's 10 minus 5. The time interval is 5 seconds, ux vera, during this change in velocity. Therefore, I have 8 minus 4 over 5. Mela jiġina 4 divided by 5, mela għanna 0.8, għaniktibha ftit isfel. And the units of velocity are meters per second. The units of time are seconds, therefore meters seconds to the minus 1, seconds to the minus 1. Nux hekk jiġu. Taqblu miegħi. Therefore, it is 0.8 meters second to the minus 1, 0.8 meters per second squared. So what I'm saying here, therefore I have 0.8 meters per second. So I'm saying the velocity is changing by 0.8 meters per second every second. Ekket ngħid. Alright? The velocity is changing by 0.8 meters per second every second. Now, acceleration is a vector. Alright? So we don't have a version of the acceleration which is scalar. We don't have that. Alright? Acceleration is always a vector. This is always a vector. So it always has a direction. So in my case, since the acceleration is positive, as I said for the velocity and for the displacement, the signs represent only the direction. So if I have positive acceleration, it means that the acceleration is pointing to the
Right.
To the right. So if I draw a vector representing the acceleration, it should be pointing to the right, and it's 0.8 meters per second squared. Sawnek okay? Sawnek alright? Issa. Alright. Let's discuss a little bit something which is very, very important. You need to understand this as clearly as possible. Alright? Mela. The sign of the acceleration, I have already discussed this a little bit in the tutorial. The sign of the acceleration does not show if the acceleration is an acceleration or if it is a deceleration. Ismawa sewdi. Because it's different from what you did at O level. At O level you used to say, if the acceleration is positive, therefore velocity is increasing. If the acceleration is negative, therefore velocity is decreasing. Wux vera tnejt sew jew le? Wux vera, kulħadd alright? That is not true. Alright? Li hija l-istess problema li għattilkom l-aħħar darba. Because at O level we used to take velocities always as positive, but velocities are not positive always. Ħantikom eżempju. Kif jista' jkun ikollok acceleration which is positive, and actually it's a deceleration. Ħantikom eżempju kif. Mela, ara. So, let's say I have this vehicle, and it is moving at 25 meters per second in this direction. And after some time, so this is at time 0 seconds. After 15 seconds, the velocity is 10 meters per second. Alright? Okay, Sawnek? So it is clear that the object is moving to the left, wux vera di darba. And what's happening to the velocity? Velocity is Isa. From 0 seconds to 15 seconds, what's happening to the velocity?
Increasing.
Increasing, għatli. Jew decreasing.
Decreasing.
Decreasing, it's decreasing, wux vera tonqos. Edin niftehmu jew le. Tajjeb? Mela, meta l-velocity tonqos, aħna x'insejħula? Isa.
Deceleration.
Deceleration. So I have a deceleration. Issa. Let's calculate, but I can't calculate the deceleration. Għaliex I can't calculate the deceleration? Because there does not exist it does not exist a physical quantity for deceleration. Fil-formula sa linear motion li intom kontu għamiltuhom diġà ħanerġgħu narawhom, we only have one symbol which is A for acceleration, mhux vera. Taqblu miegħi? Għad notajtu. M'hemmx symbol għal deceleration, kull m'hemm għal acceleration. So, let's find the acceleration in this case. Mela, acceleration is the change in velocity over the change in time. So, I'm going to subtract the final and minus the initial. In this case, which velocity is the final velocity? Attenti għal ħin. Which velocity is the final velocity?
It-10.
It's 10. And the initial velocity is the 25, wux vera. Therefore, jekk ħanamel final minus initial, mela ħanibdew bil-final. Final, am I going to write it plus 10 or minus 10 in this case?
Minus.
Minus, because it's pointing to the left. We said that the signs only represent the directions, wux vera. Therefore, I have minus 10, that's the final, minus the initial, and the initial is, what's the initial vector? Plus 25 or minus 25?
Minus 25.
Minus 25 over the change in time, and the change in time I have 15 minus 0, it's going to be 15 this time, which ver. So if I work it out, I have minus 10 plus 25 over 15. Mela għandi għandi 15 over 15, ek tiġi. Mela tiġina 1 meter per second squared. That's the acceleration. Issa. If the acceleration is 1 meter per second squared, it's positive, it's not negative. What does it mean that the acceleration is positive? Isa. that it's pointing to the right. Very good. So what I'm saying here is that the acceleration is pointing to the right. So it's pointing to the right and it's 1 meter per second squared. Now, does this make sense? We said that we have a deceleration, but the acceleration is positive. How can be that a positive acceleration represents a deceleration? Araw kif, attenti, ħarsu ftit law, please. Ħarsu ftit law, għax di importanti. Look, to decide if an acceleration is increasing or decreasing speed, don't take into consideration just the sign, because the sign is just the direction. What you have to do, you have to compare, you have to compare the direction of the velocities to the direction of the accelerations. Look, in this case, the velocities are pointing to the left, tarawhom, but the acceleration is pointing to the right, so they are in opposite directions. If the acceleration is in the opposite direction to your velocities, it means that instead of increasing, it will decrease your velocity. Għaliex? Because I'm saying that the velocity is moving to the left, but the acceleration, the acceleration is telling us that the velocity is changing in the opposite direction. So if I have 25 meters per second, every second I'm reducing those 25 because I am changing the velocity in the opposite direction. And when we have vectors moving in opposite directions, alright, the result would be that the magnitude decreases. Alright? So, mela attenti. We only have one acceleration. We only have the physical quantity acceleration to calculate. You have to calculate the acceleration. After calculating the acceleration, the sign only represents the direction of the acceleration, only represents the direction. Then you have to compare. If your acceleration is in the same direction of the velocities, as in this case, look, as in this case, the direction of the acceleration and the direction of the velocities, they are in the same direction. So the acceleration is increasing my velocities, so I have acceleration. But if the acceleration is pointing in the opposite direction of the velocities, the acceleration will decrease my velocities. And in fact, I have a deceleration. Remember, the acceleration only shows by how much the velocity is changing and in which direction it is changing. Alright? So if the acceleration is showing that the velocity is changing in the opposite direction of your velocities, the result would be that your velocities would decrease. Therefore, you have a deceleration. Now, we have to use this idea in any direction. So if we have vertical velocities and accelerations, we have to use the same idea. Alright? So the sign of the acceleration does not show if it's an acceleration or deceleration. It just shows the direction of your acceleration. And here, I think we have a very, very clear example, alright? Where we obtained a positive acceleration, but actually it's a deceleration. Sawnek alright? Jew le? Naf li l-metodu jinstama stramp, għajdli Matthew.
If on the diagram,
Aha.
the 1 meter per second is pointing to the right, how is it still deceleration?
Mela, if the velocities were pointing to the right like this, and we had a deceleration, then the result would be an acceleration in the negative direction mbagħad. Għaliex inti jekk il-veloċità qed tonqos, jiġifieri jekk kienet 25 meters per second u kienet 10 meters per second and the time interval is 15, ara kif vera. Jekk nipprova nsib l-acceleration issa ħad tiġi final plus 10 because it's pointing to the right now minus 25 which is positive because it's pointing to the right over 15. So I have minus 15 on 15 and the answer would be minus 1 meter per second squared. So in this case, the acceleration is pointing in the opposite direction of the velocity. So the velocity would decrease. So the rule that if the acceleration is pointing in the opposite direction of the velocities, it's a deceleration, it's always true. Fimta, Matthew? Alright? Ġifiri, as such ma tridux toqgħodu tinkwetaw intom, aħdmu d-domanda. Aħdmu sew, araw li tużaw plus vectors to the right minus għal vectors to the left, and the answer will show you exactly in which direction the acceleration is pointing. That's all. Alright? Imbagħad intom tridu tinterpretaw ir-riżult. Imma toqgħodux tinkwetaw għax ġi positive jew aħdmu u mbagħad tgħidu tagħmel sens jew le, iċċekkjaw jekk qegħdin kontra xulxin u qed tonqos il-veloċità tagħmel sens. Jekk qegħdin favur xulxin u l-veloċità qed tiżdied, tagħmel sens ukoll. Alright? Fimna? Now, okay, let's continue. So, one last thing about the acceleration. The acceleration, the formula that we have just done, change in velocity over change in time, has again the same constraints as the formula for the velocity. So if you're using this formula, change in velocity over change in time, this is correct only if you have a uniform acceleration. A uniform acceleration means that in this period of time, the acceleration is changing at a constant rate. Alright? At a constant rate. Mela, for example, if I have 2 meters per second squared, it means that every second the velocity is changing by 2 meters per second continuously. Alright? If it's steady, if the increase in velocity or decrease in velocity is steady, alright, that's called a uniform acceleration. Sound alright? But if the velocity is changing all the time and the rate at which it is changing all the time as well, so the acceleration is not constant, these types of situations are a little bit more complicated, alright? Because we don't only have the velocity which is changing, but even the acceleration. So the velocity is changing at a different rate all the time. When we have these types of situations, we're going to discuss one of these situations during the next topic, alright? And you're going to discuss one of these situations as well with the waves lecturer when you start SHM. Alright, ma bdejtuħ xu SHM naħseb. Meta tagħmlu SHM, meta tibdew SHM, hemm sitwazzjoni fej għandek acceleration qed tinbidel ukoll. Now, when it is changing all the time, this formula is not good to calculate the acceleration. So we have to calculate the instantaneous acceleration, which is the acceleration at an instant in time. And again, as for velocity, we have another formula. We write it a little bit different. dv by dt. dv by dt, d means a very, very, very small change in velocity over a very, very, very small change in time at an instant in time. And again, we're going to see how to find an instantaneous acceleration when the velocity is changing at a different rate all the time later on. Alright? Again, this is the most official formula because it's the most formula in general. We can use that even when the acceleration is changing all the time. Mela, alright, so that was the introduction. So in the introduction we discussed displacement, we discussed velocity and accelerations, which are the three most important okay, hawnhekk hija Jake. Alright. Issa mbagħad Jake, provara il-recorded lesson tal-ewwel biċċa. Mela, so we discussed the three most important physical quantities that we're going to use throughout the whole topic, alright? Displacement, velocity and acceleration. The three of them are vectors. Be sure to use the signs to represent the direction, plus to the right, minus to the left. Issa, the next part of the topic, in the next part we're going to start drawing graphs. Why is it very important in linear motion to use graphs? Because in many cases we have journeys. In many of these cases we're going to discuss about journeys. Alright? And when you have a journey, for example, you have an object, it starts from rest. What does it mean when I say starts from rest? Isa. At rest, xi tfisser?
0 meters per second.
0 meters per second. We can say at rest or we can say stationary. Both of them mean the same thing. So if I have an object which starts from rest or it's stationary, then increases velocity, so we have an acceleration. Then it continues on moving at constant velocity, then decreases velocity, then increases. If you have a journey like this, which is made of different parts, where the velocity is changing, it's moving at constant velocity, etc., but it's changing all the time, it is very difficult to visualize the situation if I just use words. So instead, in linear motion, we use a lot graphs to represent what's happening in this situation. Since we have 3 different physical quantities, we have 3 different graphs that we can use to represent a journey of an object. Alright? And therefore, I'm going to start with the first type of graph. So, if I, first of all, in the notes you have all the definitions needed and the formulas, alright? So for velocity and for acceleration, okay? Now we're starting the part regarding graphs. So let's start with the first type of graph. The first type of graph that we're going to discuss is a displacement time graph. Displacement time graph, okay? So in these types of graphs, we're going to plot on the y-axis displacement s in meters, and on the x-axis, we're going to have time in seconds. In these 3 different types of graphs that I'm going to discuss throughout these lectures, the x-axis is always represents time, always. Alright? The x-axis always represents time. Edin niftehmu. Okay? While the y-axis represents then the quantity. Issa, as you can see, on the y-axis I have at 0, obviously, 0 displacement. Now, what does 0 displacement means? Anara. Attenti, this is displacement, it's not distance. So we have direction. What do you think does it mean that we have if I tell you, look, right now the displacement is 0. What does it mean, 0 displacement?
Constant tower.
Le.
At rest.
Attenti, laqqas. Attenti, jien m'għandix velocity time graph. This graph is not giving us information about the velocity. Tajjeb li għattu di, għax dan huwa żball normalissimu li jsir li huwa żball gravi. If the graph is a displacement time graph, this is not a velocity time graph, so I'm not telling you what is the velocity at this time. I'm telling you what's the displacement at this time. Mela, ħaninkom ftit. When we measure displacement, which is a vector, it's the distance, it's the amount of meters covered in a certain direction, the displacement is always measured from a point, from a fixed point, which we call normally a reference point. Ux vera? Diġa konna diskutajni ftit di fil-bidu. So when you measure displacement, we always measure the displacement from a reference point. Issa jekk ħassaqsuni which is the reference point, dik issa nispjegaw iktar qudiem meta nibdew naħdmu d-domandi, xe reference point kultant skont id-domanda. Alright? Imma lissa l-importanti li tafu li displacement is always measured from a reference point. So if I say that I have 0 displacement, what does it mean, issa 0 displacement? That I am where?
At the reference point.
At the reference point. Ġifieri jekk jiena għandi graf li tibdili mid-0, jew inkella pereżempju għandi graf qiegħda hekk, mela qiegħda kontinwament fuq id-0. Xi tfisser? Li as time goes by, my displacement remained always 0. So my object is always at the reference point and it's not moving. Fimna? Alright, sissa. Mela, ħankomplu. Dak l-x-axis. Alright, now let's say that I have these values 10, 20, 30, 40. u hawnhekk għandi 20. And this is my graph. Mela. First of all, you have to notice that the graph can be positive and negative. Alright? If the displacement is a positive displacement, it means that I am measuring the displacement from the reference point to the right. Hekk tfisser positive displacement. If I have a negative displacement, so if the graph is in the negative part, and I have therefore negative displacements, it means that the displacement is measured from the reference point to the left, because the arrow, the vector, is pointing therefore to the left. That is the negative displacement. So in this graph, you will know exactly the position of the object, where it is, with respect to the reference point. If it's positive, it's on the right of the reference point. If the displacement is negative, it's on the left of the reference point. Sawnek alright? Kulħadd alright issa? Eh? Mela. So let's try to interpret this graph. Issa. When interpreting graphs in linear motion, the worst thing to do is to learn the shape of the graphs by heart. That's the worst mistake that you can ever make. Alright? You need to read the graphs. Għaliex qed ngħidilkom. We're going to have 3 different types of graphs, and all of them have similar shapes. If you try to study the shape of the graph, you will start mixing up one graph to another, one type to another. Alright? U ħatamlu geġwiġija sħiħa. So you have to read the graph. As you read a sentence, you need to read a graph. How are we going to read the graph? You read the graph by first reading the first point and the final point of that line. Xiġifieri? Mela, ejja ħanaraw. So, at 0 seconds, because this is 0 seconds, alright? What is the displacement at 0 seconds in this case? ħanħassrilkom diħa li ma tħawwadkomx. Where is the graph at 0 seconds, Isa? What is the value of the displacement at 0 seconds? Il-graph hija l-blu. Isa. Ejja. At 0 seconds, how much displacement I have?
20.
20 plus 20. So, at 0 seconds, so if this is my reference point, at 0 seconds, can I say that my object is at the reference point? If the displacement is 20 at 0 seconds, qiegħed fir-reference point l-oġġett? Mhux qed nifhmek Maraja. Le, eżatt, proset, thank you. Mela, at 0 seconds, the object is not at the reference point because the displacement is not 0, the displacement is plus 20. So plus 20 means that it is at 20 meters away from the reference point to the right or to the left?
The right.
To the right. So my displacement at 0 seconds, it's like this. 20 meters to the right. So my object is at this position. The object is 20 meters to the right of the reference point at 0 seconds. Now, as we continue, at 10 seconds, it's plus 20. At 20 seconds, it's plus 20. At 40, it's plus 20. So, if during this amount of time the displacement always remained plus 20, so is the object moving from this position?
No.
No. Therefore, if I interpret the graph, I can say, therefore, the object is not moving, so is at rest 20 meters away, 20 meters to the right of the reference point. Fimna? This is the way how you have to read the graph. Din hija kif taqraw l-graph. Alright? Taqbad l-ewwel punt, taqbad l-aħħar punt u tara x'ġara in between. Jekk tara li l-oġġett baqalek fl-istess punt mela dak ma tċaqlax. Ħa nintroduċi di u niqafaw. So, let's draw again the graph, all right? So that's time in seconds, that displacement in meters, 10, 20, u għajja nejdu 40, 30, 20, 10, 0, 0. And this is my graph. Now, this is my graph, alright? Tajjeb? Mela. Kem ninterpretaw l-ewwel biċċa biss. At 0 seconds, what is the displacement at 0 seconds in this case?
0.
0. So, where is my object at 0 seconds? Isa, it is at
Reference point.
At the reference point, very good. So at 0 seconds, since the displacement is 0, alright, my object is at the reference point at 0 seconds, okay? But if I move to the last part of the graph, which is this part, at 40 seconds, now the displacement is how much?
20.
20 plus 20, so we are 20 meters away from the reference point to the right, ux vera. So my object after 40 seconds is at this position. So was the object at rest in this case? No, it is moving and it is moving to the right. So I can start interpreting this graph as the object is moving to the right. Issa mbagħad baqa' li xnajt, issa nkomplu għada. But for now I can say that the object is moving to the right. So from the graph, from a displacement time graph, you know exactly the position of the object at each time, at every second, you know exactly the position, and from the position of the object, you can then interpret if the object is moving or not. Alright? Tajjeb? Ħanħallikom hawnhekk narakom għada. Okay?
Bye, thank
Ciao,
you, sir.
ciao,
Thank you,
ciao.
sir. Bye.
Thank you, sir.